Hey, I'm back. So, mostly just going to start today with adding some documentation to this code. So, last time I did this offline, but I thought, why, might as well just do it on stream as well. So, this is just going to be some copy pasting at first and adding some comments. So, this is for cancel orders. This one doesn't even have a return parameter. Oh. Right. Like I said previously, order IDs can be found using the API, but I'll show that a little bit later. When I make, I'm probably going to make just a basic command line tool for interacting with IMX at first. So that's probably what I'll start working on once I've finished making these function definitions. So there's one more for buying cards or for buying NFTs. So that's one that I'm still going to make, and then I'm probably just going to continue with just making a basic application. Okay, looks fine. I'll just say 4 Ethereum. Should still be updated as well. Creating the transfer. Just copy paste this. Okay. Let's see. Let's copy this. Oh, wrong one. The ID cannot be a hex string, so that's wrong. Yeah, this is wrong. Okay, let's make the final method for buying things. Let's see. We'll just go into the function definition here. Oh. I'm back. Got a phone call. Sorry about that. Okay, let's see. Where was I? Oh yeah, the oh, damn it. This is the one I needed. Oh. Hope. No. Let's copy this out. Order ID. Yeah. Looks good. Order ID, I can copy that from the cancel order. And we also already wrote the code for the fees, so we can copy that as well. Do we do that here? Oh yeah, just see double price and then I'll just copy that, it's easier than writing it again. Oh. Oh. Right, let's see. Or, right, yeah. Okay. Okay, so let's make sure this is correct. Order ID, address, the ID, token ID, price, fees, fee length, and the key followed by buffers. Yeah. Okay, great. Okay, so we're not going to be testing this one immediately, just after I've actually implemented it in a little bit more of an application, because in order to test this I would have to actually buy something. So I'm not going to do that now. But let's create some documentation first. Okay, what did I write for the fees in earlier method? Okay, well, yeah. I mean, that's good enough. Okay. I mean, of course, price and token ID should match the actual order as well as the NFT ID and the address. Otherwise, the order itself won't be able to you won't be able to file an order that's incorrect, of course. But I'll show you how to use this a little bit later on. Okay, I think that was the last method I wanted to implement. If we go here, okay, so generate key, we've done get address, sign message, registering addresses, canceling orders, trade fee, buy, sell, and transfer. Yeah, okay, so for now I think everything's implemented. So the next thing that I wanted to focus on was storing private keys. Because of course, if we're going to be using this, or in order to use this, you need a private key for an address, and it's not really that big of a deal if it's kept, well, I mean, of course it needs to be in memory when you are actually using it, but if you actually want to store a wallet, you don't want to do this in plain text. Even though probably nothing will go wrong, but still. Probably better not to do it that way. So I'll create a new module. I'll call it key loader or something. Right, let's make this startup file for now. And we'll close that one for now. Okay, but at least we finished implementing methods from the library. So that's nice. Let's make a quick main function. Oh. Let's do hello world again. Always a good place to start. And that runs just fine. Okay, so probably the best way to do this is to do AES 256-bit encryption on the key itself. So now we just need a way to derive a key, an encryption key from a password, and then use that key. So we can use pbkdf2 for generation of passwords. That's really just a function that intentionally takes a while, it just loops through the same hashing function a large number of times, just to slow down any attempts at guessing potential passwords. So you can make it as slow or as fast as you want, but the faster you make it, the less safe it is, of course. So yeah, let's see how we're going to make this. So first, there should be a function to get an encryption key. Let's call it get encryption key, and we'll give it a password. And now, if you only use a password, then what someone can do is just create a table with the associated key for every password, and then they can just reuse that every single time. So what you want to do is pad the password with a bunch of random data, so that you cannot make a table that contains pretty much every password out there, because every password is going to be way too long in order for it to be on that table if you include the random data at the end. Of course, the random data itself is not kept secret, so it's only used to protect against these kinds of attacks where you keep a table of potential passwords with the associated encryption key. But we use something called a salt for that, which is just random data. I think this pbkdf2 is in, I looked it up previously, it's like in crypto.cipher, and then oh no, it's in protocol. pbkdf2. Yeah. And then we'll just do pbkdf2 password. And the salt, 32 bytes. And so this is just how, the higher this number is, the safer it is, but the higher you make it, the longer it takes. 10 to the 6th, I think, is fine. Oh, it's not finding the function. PBK. Oh, PBK df2. Yeah, so password. Yeah. Okay. Yeah, so of course we're going to need a random. We can do. How does this work? Is it just new or? Yeah, I think it's new, right? Yeah, then we just read 32 bytes, and that's the salt. Password or something like. Yeah. Okay, so that should give us a different key every time, of course. Yeah, and as you can see, it takes a little while before it actually shows a key. And that's how long it's going to take to test one password if you were to try and crack passwords generated with this. So, of course, if I change the iterations, if I make it like 10 times higher, then now it'll take a very long time before it actually shows as a key. Yeah, there it is. But that's like annoying. And I think 10 to the 6th is fine. You want a time that's okay for if you're just typing in your own password and you only have to check one, but it's way too long if you want to try to crack passwords, for which you would need to use, well, test a ton of different passwords. So I think this I think takes like half a second or something probably. We can test actually. Oh. Time, I think. Perf counter. We can test how long this takes on my PC. Yeah, so slightly over half a second. No, I think that's fine. That's short enough to not be annoying, but too long to try cracking passwords with. Okay. Let's see. Okay, so next up will be encrypting and functions for encrypting and decrypting data. So we can generate keys. Now we just need to be able to encrypt and decrypt strings with them. So data and a key. And we'll just make the same function for decrypt. Okay. Okay, so data is just going to be in bytes. So let's make like a test string. Make a byte string that just says hello. That's going to be the data we'll be encrypting and then decrypting again. Now, I looked up how to do this a little bit before, so I think the first thing you need to do is add the message so it has the correct length for the cipher for AES. So first of all, we'll need to do some imports for that. So from crypto.cipher AES using. Okay, that should be all we need, I think. So we'll do that length. We'll just do that length. AES.block size. Okay, so the amount of data we have needs to be divisible by the block size. So we'll do AES.block size minus the length of our data modulus block size. Okay, and that should tell us exactly how much padding we need to add in order to make the block size divisible. So let's test. Let's print block size. I think it's, how much was it again? Oh. $16, okay. And how much do we have? 12, okay, so it should add 4. Yeah. So this will add 4 characters in order to make it 16 again. So let's generate our padding data. And that's just going to be padlen. We'll just put it in an array, I think. It's to be a byte array. go. Okay, so the reason we do this is so that once we actually decrypt our data again, we can know exactly how many bytes of padding are added by just reading one byte and then seeing what it says, and then we can remove that many bytes from our message to remove the padding again once we've decrypted the data. Okay. So our data is going to be we did a nonce as well for this. So we need to store the nonce as well. So in order to be able to decrypt the data again later. Oh, hang on. I didn't actually define the cipher yet. as.mode cbc, oh, bc. And of course the nonce needs to be there. So I don't know exactly what. I sometimes have to look things up real quick, so you'll probably notice that when I delay it, when I stall a little bit. But I think this should work. Yeah, and we can probably just do a base 64 encode of the data and return it that way. So base 64 import b64 encode b64 decode. There we go. Oh, hang on. Yeah, of course, I put this in the wrong spot, but it does seem to be working. For a second there, I thought it wasn't encrypted, but it is. Yeah, so this is our encrypted message. And we should have the... Well, let's remove these print statements. Okay, well, let's decrypt it again. So first we basically just do these steps in reverse now. So let's decode our data first. So data encrypted. We'll get the nonce. And so until we'll read one block of data for that. Did I do something wrong? Oh, spelled it wrong. We'll define the cipher again. New. Our key. Dot mode. CDC. Nonce. And now decrypt the data. Of course, skipping the nonce. And now we can recover the pad length by getting the last byte. Now what I saw other people do here was a quick check using the pad length to see if the decryption was successful. So we can check if so we just get the actual padding data and we check if that's equal to what we should have set it to, so pad length multiplied by pad len. And if that's not the case, then we'll just return an error or raise value. We'll say incorrect password. Okay. Or incorrect key, actually. Encrypted. Right. Let's see if this works. Ah. We're missing a character. What's happening? What did I do wrong? Okay, let's see. Figure this out. Oh. That should take off from the end, not return the length of the padding. Of course. That's why we only got the first few characters. Okay, but that works now. So now let's make it so that we can actually use a password for this. Or well, actually we can already do that. So what we just need to be able to do is store the salt as well as the password. And then we can store a key in a file in a way that it can only be read if you have the password already. So for storage, we're just going to use pickle. And for requesting sensitive data, we'll use getPass from getPass. Okay, so we have our functions for encryption and decryption. Let's make a few for saving and loading wallets. Next. So, and that takes an ETH key as well as a password. Now what I would like to be able to do is see the actual address associated with this key without needing the password. So first we can get the address. So we'll import from IMXlib. Get address. So we'll calculate the address first. Then we need a salt. And this is all data that's going to be public within the file that we will use for loading the wallet later. The salt you need in order to decode the encryption key, or to decode the wallet key using the correct password. So let's encrypt this. Let's turn that into bytes. So this should just be a number. That should be a string. Oh, str, sorry. Yeah, it should work. So then we can do key, using password and salt. There we go. And now we'll just open a file for storing the wallet. Let's call it wallet underscore and then the address. And we'll just do .wlt or something as the extension. Of course, the extension doesn't really matter. It's easy this way. And we will write by binary. go. We'll dump the address first. Then the salt. Oh, we need to specify where it should go, of course. What file? And then the actual encrypted data. And then we can just return, or well, don't really need to write that explicitly. Or no, just file name and password. Both strings. Reading bytes this time, or reading binary this time. And we'll do we don't need the address in this case. Just get rid of it. And then we'll read the salt. And the encrypted data. Or password. Salt, recover the encryption key. Actually, just decrypt this first. Oh, yeah. And we'll convert that into an integer. Big. And we'll return that. Okay, so we'll also make a function for just recovering the address. And that just takes the file name. We don't need a password for that because it's in plain text. There we go. Or maybe it's nicer to do it this way. Don't think it matters, but okay. Let's see. Let's remove this. let's import generating keys. Let's just generate one. So that just gives us a random key every time, as it should. Let's see if we can store this. Save wallet key, and we'll use hello, or let's just do password. Password. Okay, let's see if it's stored. Okay, I'll show you my desktop. So it created this file right here, wallet underscore together with the wallet address. We just open this in Notepad, see what it looks like. Yeah, so it just looks like a bunch of random data. So in actuality, what it starts with is the wallet address, but it's binary, so we can't really read that. Followed by a bunch of random data that's the salt that's needed to decode the rest, the actual key stored in this file. And then this last part should be the encrypted key. So let's see if we can actually recover the key from this. So the file that's what it's called. Let's comment this out for now. Let's do load wallet address first. Let's make that a hex string so we can actually read it. Yeah, and that's exactly what's also stored in the title or in the name of the file itself. Now let's get the actual key. Password. Okay, so that should be the private key that we stored. Let's see if we get if we give it an incorrect password, it should error out. Yeah, so it gives us a value error, incorrect key. Okay, great. So that works. Now let's just make a prompt for creating and storing passwords, or creating wallets and storing them. Prompt. I tried my best to plan this out a little bit, but I'm still struggling, so. Oh, we need OS in order to be able to do that. Minus directories. Now we'll check every WLT file in the folder. Okay. And now let's print every wallet address that we can load. Oh, hang on. Needs to be the length, of course. Should look fine. Why does that not work? Why is that not working? Oh no, well, it's fine. Makes more sense this way, I think. Oh yeah, of course, it still prints it as a decimal number. There we go. And this should probably start counting at 1. And at the end, we'll do another print for adding a new wallet. We'll do looks good. We'll get an input. And we'll just do a while true loop until we get a valid choice. We'll break if we get a valid response. Oh, and we need to take into account that the input may be invalid. Oh, not catch accept. So let's request the password. We'll check if it's correct, and if it's not, we'll ask again. Get pass. Let's list the local address. So I can type in here, but you won't see it in the actual command prompt when I type. So that's what the what getPass does. So that's better for entering passwords this way than to just have it echoed in the command prompt. Let's say the wallet, actually. Let's get our private key. Copy this brief. Yeah. Otherwise you get the incorrect key and it crashes, okay. Yep. Let's just break out of here. Return the private key at the end. That works. Okay, so now we just need to do something else if we chose the add new wallet option. You can just ask the user to enter this. And we'll just allow the user to leave it blank for a random key. And we'll just say type characters hidden, just to make it clear. We'll test if no characters were typed, and we'll say ethref. We'll generate a random key. And then we'll say if not. Oh, is instance. Just to make sure it needs to start with 0x. Or actually, no, it doesn't need to. No, that doesn't need to here. It'll work either way. We'll tell the user what they're storing exactly. There we go. And we'll then request password to use. No, we don't need that. And we'll ask the user to enter again. And we'll check if they're the same. And we'll break out of the loop. Else we'll print and if it did work, then we'll save the wallet. We'll print a message saying go. And this we do otherwise. Let's see if this works. Oh, did I set it to print the result? Yeah. It's wrong. Yeah. Yeah, and it prints the private key. If I add another wallet, I'll just type nothing. Key for address. The password again. Okay. Is that in fact a random one every time? Yeah. Okay, and now I should be able to load any of these keys by entering password. Yeah, seems like it works. Okay, cool. So now we have a mechanism for storing and loading private keys for different wallets in a way where you cannot just look them up on the disk by just opening the file in which the key is stored. So yeah, I think that's probably going to be where I'll end it for today. Been online for almost 1.5 hours now. So next time I think we'll actually start making a market application or a command line market application. So that should be nice.